arms are pivoted directly to the axis, then it becomes k is equal to 1. So usually we have the formula for k, that is tan beta divided by tan alpha. So this formula is used to find out the value of k in case any of the axis, any of the arm, whether it is maybe upper arm or lower arm, if it is not pivoted to the axis, then we need to use this equation. If both upper arms and lower arms are directly pivoted to the axis, then the value of k you can directly take it as 1. Even though you can use this formula when it is pivoted to the axis also, but finally we are ending with the value of k as 1. So it is advisable to calculate the value of k only in case when the upper arm or lower arms or both the arms, if they are not pivoted to the axis. If they are directly pivoted to the axis, not necessary to calculate. Directly you can take the value of the 1. In the first problem of yesterday's class, the upper and lower arms were pivoted to the axis, so we have taken the value of k as 1. But in the second problem, the upper arm is pivoted to the axis, but the lower arm is not pivoted to the axis, so we have used this equation of tan beta by tan alpha and we have got the value of k. So that was our second problem. So now let us discuss a third problem where both the upper arm as well as the lower arm is not pivoted to the axis of the spindle. So let us discuss the problem statement first. So I will go through the problem statement. Please understand, I am solving the problem, today's problem also from the textbook SS Ratan, and the example number is 16.4 and page number is 565. So which you can go through once again in your home. So let us discuss the last problem. This is the last problem on Porter governor. So let us discuss the problem statement. Each arm of a Porter governor is 250 mm long. The upper and lower arms are pivoted to the lengths of 40 mm and 50 mm respectively from the axis of the rotation. So this is a very, very important statement. The upper and lower arms are pivoted to the lengths of 40 mm and 50 mm respectively from the axis of the rotation. So it means the upper arm is pivoted at a distance of 40 mm from the axis, whereas the lower arm is pivoted at a distance of 50 mm from the axis of rotation. So it means both the upper arm as well as the lower arms are not at all attached to the axis of the spindle. So very, very important. Each ball has a mass of 5 kg. The mass or the weight of the ball is 5 kg and the sleeve mass is 50 kg. The sleeve mass is 50 kg and that is the capital M, and small m is 5 kg, that is the mass of the balls. The force of friction on the sleeve of the mechanism is 40 Newton. Here in this case the force of friction is given, that is F is equal to 40 Newton. Determine the range of speed of the governor for extreme radii of rotation of 125 mm and 150 mm respectively. So it means two radiuses are given, that is 125 mm and 150 mm respectively. So with two radius of rotation, that is 125 is the minimum radius and 150 mm is considered as a extreme or the maximum radius. So here also we need to discuss two cases. From both the cases we need to find out the value of the n. So if we have the value of the n, then we can find out what is the range of the speed of the governor. So how to find out the range of speed of governor? The maximum speed minus minimum speed is going to give us what is the range of speed for that particular governor. So before going for solving of the problem, let us write the given data in the problem statement. So what is the data given? So given data. So I am going to write the given data from the problem statement. The each arm of a polter governor is 250 mm long. The arm length is given. Arm length is given, that is 250 mm. Pivoted to the axis at a distance of 40 mm and 50 mm respectively from the axis of rotation. Each ball has a mass of 5 kg. So it is a small m, that is a 5 kg. The next one is sleeve mass is 50 kg. So it means capital M is given, so that is 50 kg. The force of friction on the sleeve of the mechanism is 40 Newton. That is a small f is nothing but it is a 40 Newton. Determine the range of speed of governor. So N max minus N min has been asked. That is nothing but the range of the speed. Range of speed of governor has been asked for extreme radii of rotation. So R1 I will call it as 125 mm and R2 I will call it as 150 mm. So I will call it as minimum radius and I will call this as maximum radius. I will call this as maximum radius. So two radiuses have been given. One is 125 mm and one is 150 mm. So I will call 125 as the lower value as the minimum radius and the higher value as a maximum radius. With this given data, we need to find out what is the range of speed. ROS I will call it as in short. What is the ROS? That is nothing but maximum speed minus minimum speed is going to give us what is the range of the speed. So addition to the previous problems. In previous problems, they have not given us what is the value of f. If the value of f is not given in the problem statement, then we can take value of f as 0. But here in this case, the value of f, that is the force of friction, is given as 40 Newton. So I need to consider this also in my governing equation. M is the mass of the sleeve, small m is the mass of ball, and the arm length is given for both upper and the lower arms. With this given data, I need to find out what is the range of the speed. So let us understand how to calculate the range of speed for this case. So I will call two cases. That is the case 1. So when R1 is equal to R min is equal to 125 mm. For this case, I need to draw the configuration of the governor. So let us draw first the axis of the governor. I will draw the axis of the governor. So this is our axis of the governor. So this is my radius. So here I have balls whose mass is given as 5 kg. So this is nothing but small m. The upper arm length is given, that is 250 mm. But it is not pivoted to the axis. So it is pivoted at a distance of 40 mm from the axis. It is pivoted at a distance of 40 mm from the axis. So this is my axis. Similarly, so this length is known for us. This length is given as 250 mm. This length is known to me, 250 mm. The next, the lower arm is also 250 mm, but it is pivoted at a distance of 50 mm from the axis of rotation. It is at a distance of 50 mm from the axis of rotation. It is pivoted. So this distance is also known, that is 250. So this distance is 250. So I will draw a dotted line here. So we know that the relation or the angle between the axis and the arm is given as alpha. So if this angle is alpha, then this angle will also become alpha, and I will extend this axis and I will draw a dotted line here. So this angle is beta because this angle is also beta. So this angle is alpha, this angle is beta. So this distance is known to me that it is 125 mm. 125 mm. So this is the first case, and similarly for the case 2 also I need to plot the configuration, or I need to show the configuration. In the examination, it is always preferable to draw the configuration of the governor so that the examiner can understand. So whatever the dimensions you have shown, whether they are correct or not. If the dimensions are correct, then your calculation goes very easily. So it is always advisable to construct or show the configuration of the governor. So this is case 2 when Rmax or R2 is equal to Rmax is equal to 150 mm. So for this case, I will draw once again the configuration, or I will construct the governor. This is the axis of the governor. So this is the axis of governor. So this is also axis of governor. So this is also axis of the governor. So I need to show the radius. So this here I have attached the mass balls whose weight is 5 kg. So it is attached at a distance of 40 mm. This distance is known. This distance is 40 mm, and this distance is given, that is 250 mm, and the lower arm is attached at a distance of 50 mm from the axis of rotation. So this distance is known, that is 250 mm. So this radius is given, that is 150 mm. So I will draw one dotted line here, so to make it as a triangle so that it will be helpful while going for the calculation, and I will call this angle as beta. This angle is alpha and this angle is beta. So construction is done for both the cases. When the radius is minimum, that is 125 mm, I have constructed the configuration of the governor. When the radius is 150 mm, that is for maximum radius also, I have constructed the configuration of the governor. In both the cases, everything is same except the radius. In case 1, the radius is 150, and in case 2, the radius is 150. That is only the difference between both the cases. Whereas the upper arm and lower arm are attached from the axis at a distance of 40 and 50. So here also they are attached at a distance of 40 and 50 from the axis of the rotation. So now let us calculate what is the speed for minimum radius of 150 mm. So let us go for solution. I will go for the solution. So let us understand how to solve the problem. So let us solve it for case 1. For a minimum radius of 125 mm. For a minimum radius of 125 mm. So first I need to calculate the value of, first I will write the governing equation for the governor. It is given by mr omega square is equal to tan alpha into bracket mg plus or minus f divided by 2 into bracket 1 plus k. So this is our governing equation for the Poulter governor, where the value of m is known, the value of r is known, omega we need to find out, tan alpha we don't know. So we can find out the value of tan alpha from the figure. The value of m is known, value of g is known, capital M is known, small g is known, small f is known, k we need to find out. So it means there are three unknowns in this case. First one is omega, second one is tan alpha, third one is k. So as there are three unknowns, we need to reduce the number of unknowns in the governing equation so that we can find out the unknown terms. So to reduce the number of unknowns, as there are three unknowns, I need to reduce it to one unknown so that the missing term I can find out. So first, omega square if I consider, it is not possible until and unless I find out tan alpha and k, then only I can find out the value of omega. So it means to get the value of k, I need value of tan alpha. So it means it is advisable to start with the calculation of tan alpha. So it is advisable to start for the calculation of tan alpha. So tan alpha for first case, how need to find out? That is nothing but opposite by adjacent. Tan alpha is nothing but opposite by adjacent. So what is the value of the opposite? So this is alpha, this is opposite. So this total length is 125, but I need value only up to this. That is nothing but 125 minus 40. So that becomes 85. So divided by under root of, I need this value, that is adjacent. So I can get this value by using the values of 250 and 85. So I will get under root of 250 square minus 85 square. So what I have done is, I have used the equation of tan alpha. Tan alpha is what? Opposite divided by adjacent. So this is my opposite. So opposite is, what is the value for opposite? This entire length is 125. I need only this length. So this length is known, that is 40. So 125 minus 40 is going to give us this value as 85. So adjacent is this one. So that is nothing but under root of 250 square minus 85 square is going to give us this tan alpha, and I will get the value of tan alpha as 0.362. Similarly, to get the value of k, so what is the equation for get the value of k? K can be got by using the equation tan beta divided by tan alpha. Tan beta divided by tan alpha. So already I know what is the value for tan alpha. Now I need to get the value for tan beta. So how to get the value for tan beta? So tan beta can be obtained by using this triangle. So this is our beta. So what is the equation for tan beta? Opposite divided by adjacent. So what is the opposite value? So it is total length is 125, out of which it is 50. So I need only this value. So 125 minus 50 is going to give us 75 divided by under root of 250 square minus 75 square. So divided by 250 square minus 75 square is going to give us this value, and the value of tan beta is 0.315. The value of tan beta is 0.315. So now I can get the value of k as 0.315 divided by 0.362. The value of tan alpha is the value of tan alpha is 0.362. The value of k is 0.87. The value of k is 0.87. So now I got the value for tan alpha, I got the value for k. So now the remaining unknown is only omega. So there were three unknowns initially while solving the problem. One was omega, one was tan alpha, and another one was k. But now we have got the value for tan alpha, we have got the value for k. So now the remaining unknowns are only one unknown, that is m r omega square is equal to tan alpha into bracket mg plus or minus f divided by 2 into bracket 1 plus k. So now substitute all the values into this equation, that is nothing but m r omega square is equal to tan alpha into bracket mg plus or minus f divided by 2 into bracket 1 plus k. This is our governing equation. So substitute all the values of the equation. So small m value is given, that is 5 kg. The value of r, as we are solving it for the case 1, that is the minimum radius of 125 mm. So I need to substitute in terms of meters. So it becomes 0.125 into omega square is equal to the value of tan alpha is calculated here, that is 0.362 into bracket mg. So m is 5, g is 9.81 plus m is, capital M is given, that is 50 into 9.81. The value of F, is given, that is 40 Newton. Now the question is, the equation says it is mg plus or minus F divided by 2. So we need to take it as a positive or negative. So for minimum radius, always you have to take the negative value of F, and for positive value, always you have to take the, for minimum radius, always you have to take negative of F, and for maximum radius, always you have to take positive of F. So why to take negative and positive? Already we have discussed while doing the derivation for the Porter governor. So I will take this as minus of the force of friction is given, that is a 40, and it is divided by 2 into bracket 1 plus the value of k is given 0.87. The value of k is given as 0.87. So if you substitute and if you calculate, so you are going to get the value for omega as 16.5. So only one unknown is there. All the values are known. Only one unknown is there, that is omega square. So first you will get omega square. Then if you do the square root of that, you will get the value of omega. So now you got the value of omega, but what we want the value of n. So it is 2 pi n by 60 is equal to omega. We know that. So 2 into pi into n is not known, divided by 60 into omega is known, that is 16.5. So you can calculate the value of n as 157.6 rpm. So I will call this as n1 because it is for first case. So for the first case, you have calculated what is the value for n1. The same procedure has to be adopted for calculating the value of n2 for case 2 also, so that you can get the value of n2. So now let us understand how to calculate the value of n2 for the case number 2. So now let us do it for case number 2 for a maximum radius of 150 mm. For a maximum radius of 150 mm. The governing equation remains the same, that is mr omega square is equal to tan alpha into bracket mg plus or minus f divided by 2 into bracket 1 plus k. The governing equation remains the same. So with the same governing equation, once again here we have three unknowns, that is omega, tan alpha and k. So to get the values of unknowns, once again the same procedure has to be adopted. So first let us find out what is the value of tan alpha for case 2, that is for maximum radius. We need to consider this figure now. So this is my alpha. So if I want to find out what is the tan alpha is what? Opposite divided by adjacent. So what is the opposite value? The total length is 150, out of which the 40 is here. So it means from this we are considering the triangle, that is at a distance of 40 mm from the axis, we are considering the triangle. So this is 150, this is 40. It means what will be the length of this? That is nothing but 150 minus 40 divided by adjacent. So what is the adjacent? So this is our adjacent. So how to get the value of adjacent? Under root of 250 square minus, what is this value? 150 minus 40 is nothing but 110 square. So you will get the value of tan alpha as 0.49. You will arrive at the value of tan alpha as 0.49. So similarly, we need to calculate the value of tan beta. Similarly, we need to calculate the value of tan beta. So where is beta? So this is our beta. So this is the triangle which we are considering. So this is our triangle which we are considering. So tan beta, once again, what is the equation? Opposite divided by adjacent. So what is the value of the opposite? What is the length of the opposite? The total length is 150, out of which 50 is removed. So it means the value is 100 divided by under root of adjacent, that is 250 square minus 100 square. Minus 100 square is going to give us the value of tan beta as 0.436. 0.436. So you can calculate the value of K as tan beta divided by tan of alpha. So you can calculate the value of K as tan beta divided by tan alpha. Tan beta is given 0.436 divided by tan alpha is what? 0.49. So you are going to arrive the value of K as 0.891. So you are going to get the value of K as 0.891. So in this governing equation, we have calculated the value for tan alpha. We have calculated for value of K by using the equation tan beta by tan alpha. Now the remaining unknown is only omega. So I will write the equation of omega once again, that is mr omega square is equal to tan alpha into bracket mg plus mg plus or minus f divided by 2 into bracket 1 plus k. So this is our governing equation. Now substitute all the values into the governing equation. The value of small m is 5. Radius is 150, it is in mm. I will substitute in terms of meters. Omega square is unknown. The value of tan alpha we need to substitute. We have calculated the value of tan alpha as 0.49. So the value of mg, the value of m is 1, small m, that is 5 kg, and to value of g is 9.81 plus the capital M is 50, 9.81. So now once again the question arises whether we need to take plus f or minus f. As we have already discussed while doing the derivation for the Porter governor, for maximum radius always we need to take the value of f as positive. So I will take it as plus 40 divided by 2 into bracket 1 plus the value of k is known to us, that is the 0.891. So this is my governing equation. All the values are known. Only unknown remaining is omega square. So I will get the value for omega by calculating. I will get the value for omega square as 359.8. So I will get the value for omega as 18.97. So now the problem is not over. Next thing is we need to calculate the value for n. So how can we get the value for n? 2 pi n by 60 is equal to omega. We know this equation. So substitute all the values. 2 pi n is unknown. So divided by 60. Omega value is 18.97. So it means I can calculate the value of n2, and the value of n2 is 181.1 rpm. Now the problem is not over. The question asked is the range of speed. The range of speed is nothing but n max minus n minimum. So I will calculate the range of speed. The range of speed is nothing but n2 minus n1 or n max minus n min. Both the equations are same only. So what is the value for n2? The value for n2 is 181. Already we have calculated, minus the value for n1 is 157.6. So the value for range of speed is 23.5 rpm. 23.5 rpm. So this completes the problem on Porter governor, where both the axes are not pivoted to both the arms are not pivoted on the axis of the spindle. So this completes all the problems, all the varieties on Porter governor. So once again I will discuss. So what kind of problems or how many varieties of problems we have solved. First one we have solved where both the arms, upper arm and lower arm, are pivoted on the axis of the spindle, where if the both upper arms and lower arms are pivoted directly on the axis of the spindle, then the value of k will be always 1. Then the second problem we have discussed where the upper arm is pivoted to the axis but the lower arm is not pivoted to the axis. In that case also you can calculate the value of k using the equation tan beta divided by tan alpha. And today we have discussed the third problem where the upper arm as well as the lower arm, both the arms are not at all connected to the axis. So once again, to get the value of k, use the equation that is a tan beta by tan alpha, and you will arrive at the solution. You can use this equation also, that is mr omega square is equal to tan alpha, or you can use the equation, other equation which we have used for the problem number 1, that is the omega square is equal to 1 by mh into bracket mg plus or minus f into bracket 1 plus k whole term divided by 2. So in that case, once again you need to calculate what is the value for h using the equation of tan alpha. So this completes all the varieties and all the problems on Porter governor. So still there are many problems are there, but the variety is going to remain same. So you can refer VP Singh and other textbooks also for solving of the problem. So but the varieties are going to remain same. So this completes the problems and concept of Porter governor. So now let us discuss the derivation of Hartnell governor. For your syllabus we have 2 governors to be discussed. One is the Porter governor and another one is the Hartnell governor. So we have done the derivation as well as problems on Porter governor now. Now let us discuss the derivation part as well as problems on the Hartnell governor. So the difference between Porter and Hartnell governor is, here in case of Hartnell governor we will be having the spring. So that is the difference between the Porter and the Hartnell governor. So first let us draw or let us see the configuration of the Hartnell governor. So this shows a figure of Hartnell governor in mean position. When it starts to rotate, it moves up and then comes back to its initial position. So we are going to consider or we are going to derive the equation for the Hartnell governor when it moves for minimum position as well as for maximum position of the governor. So let us consider the axis of the governor. So this is the axis of the governor. So here I am going to draw the governor when it is moving. So here is the balls, mass balls. So in this direction the centrifugal force will be acting, and I will call this as F1. This distance I will call this as C1, and this distance I will call this as R1. That is nothing but I will consider it as a radius. I will call this point as O. I will call this point as A. And the mass of the sleeve will be acting in the downward direction, and it is given by mg plus fs plus f divided by 2. I will call this distance as A1. I will call this distance as A1. The mass of the ball will be acting in the downward direction. I will call this as m into g. And I will call this distance as B1. This distance as B1. So this is for minimum position. Now let us draw it for the maximum position. So here will be the mass ball. So in this direction the force of centrifugal force will be acting. I will call this as F2. The mass of the ball will be acting in the downward direction. I will call this as mg. I will call this distance as C2, and I will call this distance as R2. I will call this distance as R2. The mass of the sleeve will be acting in the downward direction. I will call this as mg plus fs plus f divided by 2, and this distance I will mark it as B2. This distance I will mark it as B2, and I will call this point as A, this point as O. So I will call this distance as A2. I will call this distance as A2. This is A2. So initially in the rest condition the Hartnell governor is in the mean position, but when it starts to rotate it moves up. So this is our initial condition. When it starts to rotate I have to consider for minimum position as well as for maximum position. So I will consider it for minimum position and I will consider it for the maximum position. When it is in rest it will be like this, but when it starts to rotate and go up, it will be in the minimum position like this, and in the maximum position it will be like this. So mass of the sleeve which is acting in the downward direction, I have considered it as mg plus fs plus f divided by 2. Divided by 2 because I have considered only half portion of this governor. The remaining half portion I have not considered. Only one side of the governor I have considered. So that is why I have divided by 2. So this distance is C2, this distance is C1, this distance is R1, this distance is R2. So this distance is B2 and this distance is B1. This distance is A1 and this distance is A2. So this is the governor in its minimum and maximum position. Assuming that the sleeve moves in the upward direction, we are assuming that the sleeve moves in the upward direction. So that is why I have taken it as positive. If the sleeve moves in the downward direction, then you have to consider this as negative sign. If the sleeve moves in the upward direction, then you have to consider it as a positive. So I have considered, or I have assumed that the sleeve moves in the upward direction. So I have taken it as a positive F. So in the problem statement it will be given whether the sleeve will be moving upward or downward, or some other hints may be given regarding the sign indication for f, where depending upon the problem statement what he has mentioned, based on that you need to consider either positive or negative value of the f. Either you need to consider it as a positive or negative value of the f. So F1 is the centrifugal force which is acting radially outwards, and F2 is the centrifugal force which is acting radially outwards. Now taking moment about point A, so I will call this as figure 1. I will call this as figure 1, and I will call this as figure 2. I will call this as figure 2. So from figure 1 and 2, from figure 1 and 2, taking moments about point A. From figure 1 and 2, in both the cases, from figure 1 and 2, I am going to take the moment about point A. So here is our point A. So first let us take the moments from figure 1. So this is F1, so it will be acting in anti-clockwise direction, so this will be acting in the clockwise direction, so this will be acting in the clockwise direction. So total anti-clockwise direction moments should be equal to the total clockwise moments. So first I will write the anti-clockwise moment, that is F1 into A1, that is nothing but force into perpendicular distance. Force into perpendicular distance, sorry, this should be up to this point. This should be up to this point. So that is A1. F1, that is the force into perpendicular distance, is A1. So this is equal to mg. Mg is the another one. So mg into perpendicular distance is this one, that is a C1, plus mg plus fs plus f. So I will take it as fs1 and I will take it as fs2. mg plus fs1 plus f will be equal to mg plus fs1 plus f divided by 2 into the perpendicular distance is b1. The perpendicular distance is b1. I will call this as equation number 1. I will call this as equation number 1. Similarly, from figure 2, so F2 into A2, that is the force into perpendicular distance, that is F2 into A2 plus mg into perpendicular distance is C2 is equal to, so here this is anti-clockwise, this is anti-clockwise, this is in the clockwise direction, so that is mg plus fs2 plus f divided by 2 into the perpendicular distance is b2, into the perpendicular distance is b2. But now by neglecting the obliquity of arms, by neglecting the obliquity of arms, if I neglect the obliquity, if I consider that this is in its original position and this is in its original position, then what will happen? A1 is equal to A2 is equal to A, B1 is equal to B2 is equal to B, then C1 is equal to C2 is equal to 0. So if I consider that it is in its mean position, then this will be in this condition and this will be in this position. So at that time there will be no C1 or no C2, so C1 and C2 is equal to 0. So this length is A1, this length is A2, both are equal, so A1 and A2 will be equal to A, and B1 and B2 will also be equal to B. So now substitute these values of A1, A2, B1, B2, C1, C2 into the equation number 1 and 2. Substitute the values of A1, A2, B1, B2 and C1, and C2 in 1 and 2. Substitute the values of A1, A2, B1, B2, C1 and C2 in the equation number 1 and 2. So we get F1 into, what is the value of A1? The value of A1 is A, is equal to, next, mg into C1. The value of C1 is 0. So this whole term becomes 0. So I will write directly mg plus fs1 plus f divided by 2 into b. So I will call this as equation number 3. Next, substitute the values of A1, A2, B1, A2, C2 and B2 in this equation. So it becomes F2 into A is equal to, this value becomes 0 because the value of C2 is 0. So I am not going to write this equation. So I will write mg plus fs2 plus f divided by 2 into b. I will call this as equation number 4. I will call this as equation number 4. So now equation 4, subtracting equation 4 minus equation 3. Equation 4 minus equation 3. So F2 minus F1 into A, I will take A as common. So here mg and mg gets cancelled, f and f gets cancelled. So remaining is fs2 minus fs1, divided by 2 into b, and I will call this as equation number 5. So what I have done is subtracting equation 3 from equation 4, that is f2 minus f1. So this minus this, what is going to give? F2 minus f1, A is common. So this minus this gets cancelled, f and f gets cancelled. So this is fs1 and fs2. So it becomes fs2 minus fs1 divided by 2 into b. So this is our equation number 5. So let us take fs2 minus fs1 is equal to s into h. Let us consider, or let us take fs2 minus fs1 is equal to s into h, where s is equal to stiffness of spring, and h is equal to moment of the sleeve, Then equation 5 becomes fs2 minus, fs2 minus equation 5, fs2 minus fs1 is equal to s into h. So therefore f2 minus f1 into A is equal to fs2 minus fs1 is nothing but s into h divided by 2 into b. So wherever fs2 minus fs1 is there, I have substituted as s into h. Now if I consider, so this is for the mean position and this is for the maximum position. This is for the mean position and this is for the maximum. One is for minimum position and another one is for maximum position. This is A and this is B. So this is C2 and this is C1, and we can write it as C1 plus C2 or R2 minus R1. By considering one is alpha, so this angle is alpha and this angle is beta, or you can take this as also alpha. So by considering the tan of the equation, I can write h by 2b is equal to R2 minus R1 divided by A. So it becomes H is equal to 2B by A into bracket R2 minus R1, and I will call this as equation number 6. By considering the triangles, so I have calculated the value of H as 2B by A into bracket R2 minus R1. 2B by A into bracket R2 minus R1. So Fs2 minus Fs1. Fs2 minus Fs1 is equal to S into H. So S as it is, I have the value for H as 2B by A into bracket R2 minus R1. So I will call this as also as equation number 6. I will call this as equation number 7, because equation 6 is already over. Now substituting equation number 7 in equation number 5. Now substituting equation number 7 in equation number 5, so we get A into bracket F2 minus F1 is equal to Fs2 minus Fs1. We have the equation as B by 2 into Fs2 minus Fs1. We have the equation as S into 2B divided by A into bracket R2 minus R1. So B by 2 I have written first, that is B by 2. Then Fs2 minus Fs1 is remaining. So Fs2 minus Fs1, already we have the equation, that is Fs2 minus Fs1 is equal to S into 2B by A into R2 minus R1. So I can find out what is the value for S. 2A goes this side, so it becomes 2 into A by B whole square, and the remaining term is F2 minus F1 divided by R2 minus R1. The remaining term is R2 minus R1. So this is the equation for spring stiffness. The final equation for Hartnell governor is 2 into A by B whole square, or you can write it as S is equal to 2 into A square by B square into bracket F2 minus F1 divided by R2 minus R1. So this is the final general equation which can be used for derivation of the Hartnell governor. So what we have done is, initially I have considered the mean position of the governor in the rest condition. Then if it starts rotating, then it goes in the upwards direction. So I have considered for minimum position and I have considered it for the maximum position. So mg plus Fs2 F by 2 is the sleeve mass, and mg is the mass of the ball which will be acting in the downward direction. For both the cases I have taken the moment about this point A. So here in the case 1, this is in anti-clockwise direction, these two are in clockwise direction, and for this it is in anti-clockwise direction, this is in anti-clockwise direction, and this is in clockwise direction. So both the equations I have taken the moment, and then I have simplified the equation. I have got the value for H. I have substituted this value of H into this equation, that is Fs2 minus Fs1 is equal to S into H. So the final term for Fs2 minus Fs1 is S into 2B by A into bracket R2 minus R1. So now substituting this value of equation 7 into equation number 5. So the remaining term will be F2 minus F1 into A as it is. B by 2 I have written first. Then Fs2 minus Fs1. The value is 2B S into H, that is S into 2B by A into R2 minus R1. So if I found out the value of S, it will be 2 into A square by B square into bracket F2 minus F1 divided by R2 minus R1. So this is the equation which we are going to use while solving of the problems. In the next class, we are going to solve the problem on the Hartnell governor, and that completes your chapter. So all the problems on Porter governor and Hartnell governor, I am going to discuss it from the Ratan only. So Tomorrow we are going to discuss the first problem on Hartnell governor, that is from page number 571. Textbook is SS Ratan. So if you have any doubts or any queries, you can call and contact me. We will clarify all your doubts. Thank you. This completes the derivation of the Hartnell governor. Thank you.